So let's start the fourth video in this series where we're investigating Fourier series and its application to, if you remember, our shark tracking application. Today we're actually going to talk about plotting in the frequency domain, but this is going to provide us with some intuition. Often we look at these sort of sums of complex exponentials as somewhat abstract. It's tough to visualize for a lot of people. So don't worry if we've gotten really mathematical really quick in this series of videos. Hopefully today we're going to try to connect it to something that most people are relatively familiar with. Now if you recall, in the last video we decided that we could represent a periodic signal as an infinite sum of scaled complex exponentials, which is really an infinite sum of sinusoids with different frequencies. Now in this case, the k, that's infinite, is actually just a scale of frequency. So we have this fundamental frequency. We can get 1 times it, 2 times it, 0 times it, -1 times it, -2 times it. And if you remember that when you add up a couple of these exponentials, they can actually look like sinusoids or cosine functions. And of course we're going to have scalars, or we're going to amplify them, for example, or decrease the size of them, depending on how we see fit. And depends on what type of function that we're trying to represent. Maybe we're trying to approximate a function with a sum of scaled exponentials. But as said up here, if it's a periodic function and we have an infinite number of them, we can actually not just approximate them, we can completely recreate it. Now the other thing to remember is that these scalars, we've used our orthogonality principle to come up with a great way to actually calculate them. If you couldn't remember, our fundamental frequency is also equal to 2 pi over t naught, our fundamental period. Now I started this video saying that we might want to think about how we actually visualize or take some of this abstract math and make it a bit more tangible or usable for some people. Let's look at the function that we approximated with the Fourier series in the last video. We had 2 times a cosine function plus 10 times a cosine function. And the frequencies of these two cosines were quite different. In fact, the frequency of this cosine is 5 times faster than the frequency of this cosine. If we wanted to plot this out as a function of time, we might start with, let's say, this blue one, this top one, of 2 cosine 5 omega naught t. So this term here. So that's this function here. So first off, note that it's 2 times, so it's not an amplitude of 1 that it's going back and forth from. It's 2, so you can see the 2 there. And you can also see that the frequency of this one is much higher than the frequency of the 10 cos one. So the 10 cos one is this red one here, which is obviously moving with very fewer cycles or much slower frequency than the blue one. But you can see that it is scaled by 10, and like I just said, it's going much slower than the one scaled by 2. Now the overall signal is the sum of both these cosines, which is the black one, and you can see that you've got this high frequency superimposed on the low frequency. And that's all this is. This is a sum of scaled sinusoid functions, and you can see with this black one that you can actually start to make some pretty interesting patterns. As we've said, if you have an infinite number of them, you can approximate any periodic function. So in the previous slide you saw some cosine plots, which probably should look familiar to you. We wrote out our functions of cosines. In this case we're going to write it out in things that look like terms for your Fourier series. Remember, it's the same x of t in both cases. It's just that we've taken the cosines and expanded them out into complex exponentials. And we often plot this version as a function of frequency. Now for this case, let's assume that omega naught is just 1 hertz. The first 2 terms correspond to the higher frequencies of 5 omega naught and -5 omega naught. And they have scaled values of 1. And they correspond on this interesting stem plot, which is a function of frequency, at -5 hertz and 5 hertz, with amplitudes of 1. So this term here maps to this stem. This second term maps to this stem. Now, the next 2 terms also map to 2 different stems. the frequency of 1 omega naught, and if omega naught's 1 hertz, that would be 1 hertz, has a stem of height 5, corresponding to this height, or this scaling value of 5. The last term is at negative 1 hertz, also with a scale of 5. Negative 1 hertz with a scale of 5. What I'd like for everyone to do is try to learn how to map between something that's pretty familiar with for most of us, this sort of sinusoidal as a function of time representation, and be able to map that quickly to a frequency stem plot. In this case, that higher frequency sinusoid maps to this stem and this stem, or that pair of stems. The lower frequency of higher magnitude, red sinusoid, maps to this pair of stems. Let's see if you can use that new knowledge to go back and forth between cosines as a function of time plots to stems as a function of frequency plots. They're really the same thing, so just let's make sure we note that. They're really the same functions, just being represented differently. So in this activity, I'm going to give you a plot, a stem plot, that's a function of frequency. Okay, we're going to sort of do the reverse of what we did in the previous slides. You see that there are 3 stems, and I'm asking you to plot the corresponding signal in the time domain. So they should look like sinusoids. I'd suggest you pause the video now and try to write this out with pen and paper. Are you done yet? Okay, let's move on. This is our solution. Now, to start with, let's take this pair of stems, which, if you recall, represent e to the negative 3t and e to the positive 3t. Now they're each being scaled by 2. In this case, they map to this lower sinusoid, which goes up and down around 0 from 4 to negative 4. Now, watch the fact that these are scaled to 2 in this case, but go all the way to 4 over here. And that's because, if you recall, a sum of exponentials divided by 2 will make a full cosine. Let's move on to this third stem. This one has a frequency of 0, so it's going to be an e to the 0t term. Well, that's actually just a constant. Now this one in the stem plot has a magnitude of 8. So it corresponds to a single exponential with 0 frequency, and that's actually just a straight line or a constant value of magnitude 8. The overall signal for all of these stems is this constant at amplitude 8 plus this sinusoid, resulting in this shifted sinusoid, which is basically the bottom one shifted up a value of 8. Make sure you review and understand that. You want to be really quick to move back and forth between these two types of plots. Often we think about things in the time domain, but later, and more importantly, we're going to start working more and more in the frequency domain, and we want to be able to visualize these things quickly. Let's make a few concluding notes. Remember, a lot of this was motivated by trying to figure out the speed of the shark, remember that we motivated a lot of this work by saying we want to observe the direction of the shark's head as it goes back and forth and relate that to forward velocity. And we had some data of the yaw angle of that shark's head, and from it we wanted to extract frequency. We're getting there. So our concluding notes, as we move towards that motivating example and as we build up tools that will help us figure out that velocity, I'm going to leave you with a couple questions. Was our Fourier series derivation in continuous time or discrete time? Think about it. Was everything a function of t or some discrete time step? If you think about it, everything was as a function of t, continuous time. A second question, are the smart tag heading measurements in continuous time or discrete time? If we actually measured or took measurements of the shark's heading, do we have an infinite number, or do we have a discrete set of them? We probably have a whole bunch of time-stamped measurements. So in this case, we're in discrete time. So everything we've done analysis-wise is in continuous time, but the actual data set itself is in discrete time. Let's figure out how to resolve this next time. See you then.